welcome, Amit, and yeah, go ahead with your presentation, which is about implementation and the assessment of the RP limiter in SU2. Okay, the floor is yours. Go ahead.
Yeah, thank you. So along with Dr. Praveen and Dr. Rao, I'll be presenting this work. So motivation of this work is basically we want to, this is a recent limiter by Dr. Nishikawa, and there are very few practical unstructured grid limiter in literature that have been successfully used in unstructured grid code. So just we wanted to implement it in SU2 framework and then try it out on variety of problems encompassing inviscid, viscous flow, 2D, 3D, and practical geometry case as well. So how it fares against in terms of convergence, behavior, accuracy, and what kind of time it takes against the baseline Wang-Distributional limiter. So coming to the limiter side, all of us are aware, basically you use them with second order or higher order schemes or reconstruction to prevent spurious solution near the discontinuities. So you can see an example here for a square wave problem, a textbook problem, where after some time on the left side, based on like what is the left and right function, you have an expansion and the right travels with a shock. If you use a second order scheme, for example, Lex-Vendroff, you will end up with overshoots or undershoots near the discontinuities. You need to use limiters to get rid of that. Basically, it will switch back to the first order, or it will damp out the gradients close to the discontinuities. And with the application of limiter, you can see this, it is damped out. So if you come to the various limiter functions, there are many structured limiter functions. For example, min mod, Van Leer, Van Albada, Super B, they all vary in terms of like how dissipative or compressive they are in nature and what kind of convergence behavior they have. And some of them, in fact, have been extended to unstructured grid. Van Albada is one example, which is there in SU2 also. And coming to unstructured grid, first example was Barth and Jesperson limiter in 1989. And this was the first successful application widely used in unstructured grid code. Later on, it had issues with like non-differentiability of the function. So Venkata-Krishnan limiter, which is still very popular, used across all the even commercial codes. So he uses basically, it's a differentiable function, and he treats things for the convergence to improve the iterative convergence as well. And there was a Wang modification subsequently in around 2000 or so to further improve this convergence part. But these limiters were limited to the second order schemes, and later on this Mishalak Gooch limiter was there in 2009, which worked up to like fourth order accurate scheme. And recently, Nishikawa limiter in 2022. You can see a big gaps of 5, 10, 10 years. So these limiter functions, I'll just come to what they are. And then, of course, there are some post limiter functions. They will totally disable the limiting in smooth regions. So coming to quickly, I'll go through this Venkata-Krishnan limiter. So if you have if you see the cell I have made here following our SU2 framework, which uses dual mesh. So you have a cell interface here, which will reconstruct values from the I and j and the gradients, and the left and right side, it will reconstruct. And you are limiting the gradient with this limiter function. So if it is 0, you have basically you have sorry for that, you will end up with a first order accurate scheme. UL equal to UI, it's like piecewise constant solution. And on the other hand, it's and this is basically our Venkata-Krishnan limiter function. It makes use of left hand state and right hand state, as well as the min-max values of the neighbors. So more implementation details can be found in paper, right? And there is an important thing, the parameter epsilon. So which takes care of, and you have a user-defined parameter k that takes care of the convergence behavior. So k on the higher side, basically less limiting and better convergence, but you may end up with oscillations. And k is on the lower side, means more limiting. So coming to the RP limiters, yes. Basically Dr. Nishikawa adapted the philosophy from Venkata-Krishnan limiter. The idea was to derive functions that can preserve third, fourth, or fifth order accuracy if you have higher order solver with you. If you apply Venkata-Krishnan limiter with higher order reconstruction, it will bring back to second order thing. So it won't work in the situation where we have higher order scheme with shocks. And if you apply this higher order function on second order accurate solution, you will have less dissipative solution, or it will improve upon accuracy. And in some cases, he has shown for convergence behavior. So that's what we wanted to test on more realistic cases, viscous cases, and practical ones. So this is the implementation. Again, it's a generic form similar to Venkatakrishnan he has defined. And you need to change like a few files, 4 or 5 files to implement and get going with this. I have listed on the right hand side. So this is phi function. So quickly I will say this is a dissipation, lower dissipation direction. If you see red one, this is BJ, Barth and dispersal limiter is discontinuous, non-differentiable. Venkat limiter is differentiable, but at phi should be staying 1 beyond y equal to 2, which it does not, but it's not a strict criteria, but it is desirable thing. But RP ones are less dissipative, moving towards Barth, and they are continuous, differentiable, everything. So coming to the assessment, so quickly we'll go through supersonic flow past ramp. First one, inviscid case. You can see a 15-degree ramp, inviscid case, and here oblique shock forms, and it reflects from the top wall, again reflects from the bottom wall. So if you see successively, if you notice, you will see that RP limiters are they're capturing the shock with comparatively less dissipation. If you move to the next experiment, like K value, as I mentioned, if your smaller value is more limiting, it causes convergence issues. So here you can see both BJ limiters, in most of the cases, it doesn't do good job, and it is expected also due to the nature of it. And Venkatakrishnan limiter, if you see, we have a lot of oscillation, but RP ones have converged, all of them, to the machine epsilon. And with K equal to 3, all of them, except BJ, all of them converges. And again, another important thing to notice, what the kind of time differences are there. So I have run it on this example run on single or dual core. If you have more cores, there will be differences. But here time taken, if you see from Venkat limiter to, if we go to R3, we have something like 11% extra time it takes per iteration, and furthermore R4, R5 around 12%. These are CFL history. If we take a section, I want to plot what kind of variation is coming, pressure variation over this line, over this section where oblique shock is forming, then constant region and expansion and all. So this kind of pressure variation you will get. And if you zoom in, then only you are going to notice some differences. And you can see these RP1 limiters are somewhat more compressive in comparison to Venkatakrishnan. And then the next thing is we have to cover the whole flow field regime also. Viscous case, one Rand's case I took, and typical condition I have not mentioned, but just to show they are all able to converge, and they gave almost similar results in this transonic case. And if you go to now 3D viscous case, it's a solid to wall grid around 2 million. So here this is a standard test case. Whenever I'm sick, you will have a lambda shock, this transferring back number angle of attack. So here the thing was, I had just used a Newton-Krylov solver, and the CFL condition I just kept in a random sense, not very strictly. Maybe more experiment to get the results quickly and better convergence behavior one can get. But just to see how, if you put random things like this, how these limiters will behave. So again, you can see if you might have to gauge it for a while to figure out the differences, which shocks are looking sharper with which limiter. So I think one can figure out the differences are there. And if you see the residual history, all of them, if we leave the red one, Barth and dispersion, all of them converge to 3 to 3.5 order residual drop is there. And if you see the lift history, lift coefficient, they all converge after 1200 iterations. Well, yeah. And let's say on a span of 65%, what kind of CP variation we have? It's a minus CP actually. So if you have a shock here, if you just zoom in, so clearly you can see it's more compressed in case of RP limiter function successively when cut to R3, R4, R5 together. And time history, since time integration setup, I was not very careful. And there were some, actually it would have been a better setup, but since I had result, I didn't want to run out them again. So in this particular setup, Venkat limiter was taking more time. I would blame this time integration setup for that, and other limiters took somewhat less time because what kind of CFL it is adapting to. So fair thing will be like we should keep CFL constant and then assess. But still in such kind of setup also how it behaves. And then coming like I want to cover the hypersonic regime also. This is the SWBLI shockwave boundary layer interaction case, which is from SU2 report I have taken. And the good part is that they all converge. There is no issue. And similar kind of convergence is obtained with the NK solver and up to 200 CFL also it went. And a similar kind of results we have. This is with the SST model. And you can see if I zoom into the where the shockwave boundary layer interaction is taking place, this suppression bubble and this incident shock, if you see, you can clearly see, as we have been seeing in the previous examples, it is on the shorter side. And it's like more and more of the test cases. And then it's important to see how it fares in the practical with the practical geometry. So this is a typical example of some launch vehicle, one launch vehicle where you have OJI payload fairing with small bow tail and followed by a big stage. And in between, you can see small, this dark patches. They are basically small flanges that also we have resolved. We just wanted to study the effect. It's possible with the pointwise to do it easily. So it's around a 20 million mesh with voxels in the near field. And here you can see boundary layer and small steps and all these zoomed portions. This is a Mach 3 case, an angle of attack 2, SLAU2 scheme with SA model. So I kept a CFL5 constant, CFL5 with second order solution. And let's see how the results are. So here we have Mach palettes on the left hand side. You can see various features, an oblique shock and expansion zones and many small shocks running wherever it finds an obstruction, supersonic flow, you will have small oblique shocks. And right hand side is the density contour and the nose cap region. And okay, this pressure contours in the nose cap. The thing is, usually as you go to supersonic Mach numbers, 3, 4, or even higher, a carbuncle issue appears. That is primarily it is important to choose convective flux discretization, and a limiter also can play a role in this case. So this left one is Venkatakrishnan and right is R3 and bottom is R5. So more or less like they are similar nearly, and we didn't observe any carbuncle. That's a good thing. And if you see the convergence part, so here is an interesting thing. With this set of Venkatakrishnan limiter alone, it blew out. It didn't work. While RP1 all went through, R3 R5 I tested with, so they went through and we could get converse solution. Right hand side we have like axial force history, so you can see like more or less they are very nearby and they converged. And when we switch on the Wang modification, vectorization Wang, basically it will take the epsilon correction and from whole domain it will compute the value min max and do. So it converges further, and that's the purpose of our original Venkatakrishna limiter. And I think this RP limiters are also amenable to this kind of modification and to further improve the performance. And if you see the time part, time per second, every iteration, what kind of time they take. Anyway, Venkatakrishna limiter blew out, but more or less they are like constant. They are like the time is not changing. CFL is fixed. So if we normalize it with the Venkatakrishna limiter, so Wang correction took 15% extra time, and R3 took 17% and R5 around 20%. This was run on around 200 cores. And if I just plot this cut section and windward leeward, how the CP will look like anyway over the along the vehicle. So you may see small these oscillations or jumps. They are basically all local protrusions, and that's where you get all this. If you zoom into a local protrusion, you may see small differences, but it's like again, as said earlier, on the minor reduction in dissipation. Yeah, coming to the conclusion. So this RP limiter function, it's implemented and extensively tested against multiple cases. And we tested it on a practical case also. So it's the outlook is promising. And the further interesting thing could be to test it on the like blunt body problems. Today morning we had a presentation. So with heat flux computation where things are more severe over blunt body or chemically reacting flows, how it fares. And if somebody has implemented in some branch higher order solver, they can test it with them. And the interesting thing could be to look with the scale resolving scale for like how it can help with the scale resolving simulations as well. So like last I happened to run this transonic bump case, shock interaction with one of the DDS computation. So here I think we are all look for the minimum dissipation, like even convective flux discretization also we will have dissipation functions. And this RP limiters also, whatever comes, it should be like maybe welcome thing to whatever it can improve. So with that, I am done with the presentation. Thank you. And I will just acknowledge my colleague Ajit and our group director, deputy director of the and Pedro. Thank you.
Okay, thank you, Amit. Are there any questions? Yeah.
Hi, is this available in the branch? Is this modification available down there?
So the question to you, Amit, is if the modifications are already available on GitHub.
Yeah, it's already available in SU2 8 version. It is available.
All right, great. Any other questions? Yeah, David.
Yes, I was wondering, when what kind of a geometrical case would you use the RV limiter over the magnification of limiter? Just like, would you like explain it in like in a sentence or two, like?
Yeah, so the question is if there is a case where the RP limiter is preferred over which one?
The Venkat.
The Venkat limiter.
Yeah, so like I showed in some cases, for example, in this case itself, original Venkat Krishna limiter blew out. So if you are facing convergence issue anywhere, you may give a try to it. And you are looking for a as much as low dissipation possible, like I mentioned, hypersonic cases or scale resolving simulation, you can give it a try. So they have, yes, they have little extra cost because the functions are longer, but they have added advantages over the Venkat-Krishna limiter. And the formulation is basically, a total formulation is based on like to improve upon this limiter, particular limiter. So one can try in situations, and maybe if they do work well, it is a welcome addition to the community.
I see, but like in the example that you showed.
And for sure, you can for sure try with the higher order solvers because Venkat won't retain the higher order accuracy. Higher means beyond second order. If you have solvers or somebody else adds into SU2, definitely you have to move to these RP limiters.
Does it answer the question, David, or?
Yeah, but just like in the example that you showed, the backup modification, like performed overall the best. So I was like, yeah, I was just curious, like when, like why would in that case, like why would you choose the RP over the backup speed? But I guess it's more to do with like the RP speed performed better in second order.
Yeah, I think the advantage there would be slightly less dissipation. And he
Yeah.
also said the Wang modification you could apply to the RP limiters too. So you might actually be able to, that's what you said, right, Amit?
Yes. In fact, in one of the Dr. Nishikawa mentioned this, and he was telling further more improvements he is having in mind. So I think, and this is one important component of the whole cycle, like solver part, which plays a good role and directly affects the convergence. So if we have something good in hand, that's really like helpful.
Yeah, in my experience, the Wang modification is very important
Yes.
from all the cases that I've run. So anyway.
Yes, true.
Okay. Thanks. Are there any other questions? Else, let's thank the speaker again. Thank you again.